Hello, let me describe a thought experiment to you. I also call it a dreamt experiment. I was in Germany and I was waiting for a bus in a bus stand to go to my university. There I found two charged balls beside the bus stand, and they were similarly charged, both positive. So they were repelling each other, but they were tied together with a string so that they cannot go away from each other. You might be thinking that how could one find such charged balls beside a bus stand? Come on, it's Germany, it's the country of Einstein. Jokes apart. But I thought, what would happen if I cut this string suddenly with a scissor? And then they will repel and they will go away from each other. I thought to do a small calculation. What would be the acceleration of these two particles, these two balls, immediately after the string is cut? So I took out pen and paper and did some calculation while standing at the bus stand waiting for my bus. So while standing at the bus stand, this is what I calculated. Here was one ball, here was another. Both of them are positively charged, plus Q and plus Q. Let their mass be m and m equal. Let the distance between them be r. And I knew from my school physics that the Coulombic repulsion between them is given by Q square, Q into Q square divided by 4 pi epsilon naught r square. Therefore, when the string between them is cut, the acceleration would be A equal to Q square by 4 pi epsilon naught r square, this force divided by mass. I can also write it in simpler terms as Q square by r square multiplied by some constant, call it K1, where K1 is 1 over 4 pi epsilon naught. Similarly here, this acceleration will be Q square by r square K1 by m. Okay, that was fairly easy, and I finished this calculation quite quickly, and meanwhile my bus arrived. So I went into the bus and the bus started to move, taking me towards the university. And now I am in the bus. While in the bus, I had a doubt. Did I do this calculation correctly? So I took out pen and paper once again while sitting inside the bus and rechecked my calculation. Now, while I am inside the bus, I started my calculation, and then immediately I had a doubt. I thought that the Coulombic repulsion between these two charged balls will be definitely given by this factor as before, K1 Q square by r square, but that's not all, because these two charged balls are now moving with respect to me. Actually, I am moving with a velocity maybe v towards the left, but that means these charged balls are also moving towards the right with the same velocity v. And this velocity was uniform because the road was so smooth and flat and the bus was going uniformly, smoothly. So this was a constant velocity. So I thought, now these two charges, while they are moving, they should behave like a localized current. This charge is moving towards the right, so this should be equivalent to some small localized current here at this point from left to right. Similarly, this should also behave like a small localized current I from left to right here. And when you have currents flowing, it creates magnetic field surrounding the current. So therefore, this particle which is moving and behaving like a current will create magnetic field surrounding it everywhere, and that would look like somewhat this. This is how the magnetic flux lines will be surrounding this charge everywhere, and this flux lines also pass through this other charge. And now this other charge which is moving in the magnetic field of the first charge should experience some Lorentz force. So apart from this Coulombic repulsion, there will also be some Lorentz force between them. I should take care of that too. So let's calculate that once again. So this is Coulombic force, and now the flux density at this point, call it B, created by this charge. Okay, so if I call this q as, let me label this q as 1 and this q as 2. This is particle 1, this is particle 2 with same charge and same mass. This magnetic flux is B1 because this is created by this particle. Okay, so I call that B1. What is the direction of B1? B1 will be, you can find that B1 will be perpendicular to the plane of paper, and it will be like this, going into the paper. Okay, fine. So that is B1. And what will be the value of this B1? B1 will be equal to, will depend definitely on this charge and how fast it is moving. Okay, so it depends on q and the velocity of this charge, q times v, because larger the value of this velocity, you can think there is a larger current flowing, or even this charge is larger, you can again think this current is larger, so therefore b will be more. Okay, and then divided by the distance squared and multiplied by some constant of this sort. This is the value of B1, flux density, magnetic flux density created here at this point, created by this particle. Okay, fine. Acha. Now this particle, the second particle, is moving towards the right. So I can find a force F, call it Fl, equal to Q, this Q times V, the velocity of this charge, okay, cross B1, the flux density here. Lorentz force. Okay, so this is the force that will act on this particle. In which direction it will be? That is governed by V cross B. V is towards the right, B is into the paper. So if you take the cross product, you will see the cross product points upward. Therefore, here we will have a upwards force. Okay, is upwards. You can call it FL2 because this acts on particle 2. And this is equal to QV. Now let me put the value of B1 from here. It becomes Q square V square by R square mu by 4 pi. It's a constant. Okay, so I write it this way. K2 QV by R square. And so here also it becomes K2 Q square V square by R square. This is the force acting on particle number 2 because of the magnetic field created by particle number 1. Okay. So total force, total Lorentz force, F Lorentz acting on particle number 2 is given by this K1 Q square by R square plus this K2 Q square by V square Q by R square. Okay, and this is what I calculated while sitting inside the bus and I was moving. And therefore, the acceleration which I calculated, this will be this force divided by the mass, that you can write as Q square by R square. Take it common, then you have K1 R. This should be minus, because this Coulombic repulsion acts downwards and this Lorentz force acts upwards. So there should be a minus sign there. Okay, and then minus K2 V square. This divided by O. This is the acceleration, sorry, and I divided by the mass. So this was my calculated acceleration while I was sitting inside the bus. And then I was in doubt, because previously I calculated it to be Q square K1 by R square M, and now while in the bus I calculate it to be somewhat smaller, Q square by M R square multiplied by K1 minus K2 V square. Did I do any mistake while I was standing in the bus stand? Or am I making any mistake while I am doing a calculation inside the bus? How is it possible that these two calculated accelerations are different? That's not possible. Why? Why? Because if you think of any particle in this coordinate system x, y, this position of this particle along the y direction is given by yt. This is what I measured, the value of yt, while I am standing at the bus stand or the platform. So this is the value of ypt, p for the platform. And if I measure the distance of this particle while I am inside this bus, this distance should be same. So it should be equal to YBT, B for bus. So the distance of this particle from the x-axis should be same no matter whether I am measuring it from the bus stand or from the bus from the bus. So YPT and YBT should be same. Now if I differentiate this equation with respect to time, what I get is this: dypt dt should be equal to dybt divided by dt, the derivative, and which also implies, if I differentiate it once again, the d2y dt2 p for platform should be equal to d2yb, b for bus, divided by dt2. So it implies acceleration as measured from the platform should be equal to the acceleration as measured from the bus along the y direction. But my calculation says that this acceleration, you call it AP, B for platform, is not same as AB as calculated from the bus. How is it possible? Am I making any mistake? And if I am not, then all the physics that I have studied so far in school, they are in danger. Is the Lorentz force law not correct? Is anything else in this derivation not correct? To find out that, it is your job. Thank you.